There's a second system that exhibits the same sort of oscillating behavior as a mass hanging from a spring, and that's a circuit that has some components in it. So what we need to get this oscillatory behavior is, first of all, we don't need a voltage source. We'll look later at what happens when you have a voltage source. We don't need a resistor either, it turns out. You just need an inductor, which is some sort of coil of wire. This is measured in henries. And we need a capacitor, which is some sort of parallel set of plates like this on which charge can accumulate. And capacitance is measured in farads. Actually, a farad and a henry are both very large units of inductance and capacitance. So usually these, for small, reasonable size electrical components, these are actually measured in milli or micro farads and henry, sort of depending on what your components are, or even picofarads for small capacitors. Remember, the variable that describes this situation that we used was the charge on the capacitor, which is Q. So our independent variable is Q of t. All right, now if you, one of the laws of circuits is one of Kirchhoff's laws, which says that if you have a loop like this in a circuit, the sum of voltage drops has to be equal to the impressed voltage. So there is no impressed voltage in this situation since it's 0. So we get 0 equals, and now we write down the sum of all of the voltage drops. There's no resistor, so there's no voltage drop there. The voltage drop across an inductor is the inductance times the derivative of the current through the inductor, okay, plus, and then the voltage drop across a capacitor is 1 over the capacitance times the charge that's on the capacitor, and that's Q. Now in this situation, the current I, any current that flows through the inductor is actually arriving on the capacitor as charge on the capacitor. So I is actually the rate of change of Q. And so we can express everything in terms of Q. We get 0 equals inductance times the second derivative of charge on the capacitor plus 1 over the capacitance times Q. Now, you can see this is very, very similar to our spring equation, so mass and spring equation. The mass and spring equation was mass times y double prime plus spring constant times y. So the mass in our mass spring situation is just like the inductance, and the spring constant in our mass spring situation is just like the 1 over the capacitance. So right, we did some analysis of, if you increase or decrease the mass or spring constant, what happens to the angular speed of the oscillation. We could do the same sort of analysis with our circuit now. So if we say increase, right, we know that the angular speed is the square root of k over m. We can translate that to circuit components. K is 1 over c, and m is being played by, the role of m is being played by our inductance L, so the angular speed is 1 over LC. Okay, so if we increase L, what happens to the angular speed? Well, L is in the denominator, so a larger denominator is going to make this angular speed smaller. So angular speed is going to decrease, and if angular speed increases, then the period of the oscillation increases. So putting in a stronger inductor increases the length in time of an oscillation. Okay, by the same token, if we replace our capacitor with a larger capacitor, that's going to have the same effect because this c is in the denominator, so the angular speed is going to decrease and the period is going to increase. So as we work in examples for this second order constant coefficient homogeneous and non-homogeneous linear differential equations, we have these two systems that we can use to sort of test our intuition and to use for examples. We can use a mass hanging from a spring, and we can use this sort of circuit with an inductance and a capacitor, and later we'll add a resistor and a voltage. As long as we keep in mind how these two systems correspond to each other, with just a mass and a spring, or an inductor and a capacitor, the mass and the inductor play the same role in the differential equation, and the spring constant and 1 over the capacitance play the same role in the system.